All right, so problem 2 gives us a sequence here where a of 1 is -1, a of 2 is 1, a 3 is -1, and so on. This should feel familiar to problem 23 from the previous section, where we saw the sequence here. So from this, if you remember, our formula for a of n is going to be -1 to the n. I mean, you can verify that this works for the first few terms, but it should. All right, so for part B, it asks us to compute the limit as n goes to infinity of a of n. Now, for this case, if you remember from the previous section, that this actually does not exist. If it keeps alternating between -1 and 1, it never actually approaches a limit, and thus this sequence diverges. So for part C, we need to find a formula for the sequence of partial sums S of n. So in this case, once again, it's going to be helpful to look at the pattern that we see. So S1, or this is just A1, we know this is equal to -1. For S2, we know this is A1 plus A2, and we get this is -1 plus 1, which equals 0. For S3, it's A1 plus A2 plus A3, and we see that this is -1 plus 1 plus -1, which is equal to -1. And if we do this again, we can see that S4 was equal to 0, we should get S5 equals -1. And from this, we can get this pattern here, this S of n. Now, it might help to write this as a piecewise function, because what we get is the S of n equals -1 if n is odd, and it equals 0 if n is even. And so now that we have a formula for the sequence of partial sums S of n, we can look at the limit of partial sums. And remember, the limit of the partial sums is what this series actually adds up to. Now, if we look at this limit, it turns out that this does not exist. And it turns out to be this very similar to what we did in part B. Essentially, what's going on is the sequence of partial sums changes between -1 and 0, but it never really approaches one number or the other. And so in the same way, the sequence diverges and the limit does not exist, this series also diverges and the limit does not exist.